When looking at a power plant, you may notice its odd shape. While most people can recognize a power plant with its shape, very few can tell you why it's constructed that way. Nuclear power plants are hyperbolas. A hyperbola is a function where the difference between two fixed points is a constant value. So why use this odd shape that we can so rarely see in other applications? Nuclear power plants create electricity by boiling large amounts of water to steam. The heating process they use is fission, which is when a uranium atom is split. Fission creates a large amount of heat that quickly vaporizes the water in the reactor. This steam, in turn, moves the turbines within the plant that then create electricity. Nuclear power plants are much better for the environment than other power sources such as coal or gas because nothing is burned, in turn releasing toxic chemicals into the atmosphere. Well, unless external circumstances release radioactive material as they did in Fukushima in 2012. Following a major earthquake, a 15-meter tsunami disabled the power supply and cooling of 3 Fukushima Daiichi reactors, causing a nuclear accident on March 11, 2011. All 3 cores largely melted in the first 3 days. Official cold shutdown conditions was announced in mid-December. Apart from cooling, the basic ongoing task was to prevent release of radioactive materials. Particularly, there have been no deaths or cases of radiation sickness from the nuclear accident, but over 100,000 people were evacuated from their homes to ensure this.
The reason that a cylindrical hyperbolic shape is chosen for the construction of the cooling towers on a power plant is because this shape helps accelerate its cooling efficiency. The lower half of the tower is made to be wide because it provides extra room for installation in order to make a thin film speed up evaporating cooling of the circulating water. Once the water evaporates, the narrowing of the tower helps speed up and catalyze the airflow. As it rises higher and higher and the tower gets wider again, the mixing between the heated air and air of the atmosphere helps the turbulent mixing.
To observe the hyperbolic property of cooling towers, an equation was made to fit a picture of a power plant. The equation that fits this particular picture is x minus 0.95 squared over 0.9 minus y minus 1.2 squared over 6 equals 1. As is evident, the hyperbola does not fit the cooling tower perfectly. This will happen when superimposing graphs onto images because the perspective is never dead on. Due to the translation in the numerator, this function's center is at point 0.95, 1.2. The major axis of this function is the square root of 0.9, which is plus or minus 0.94. These would be the vertices if the function were not shifted. Due to these shifts, the vertices are 0, 1.071 and 1.9, 1.071. This, of course, is just an observed and an estimated function of a 2D model for a hyperbolic power plant. In real life, these hyperbolas are actually hyperboloids, meaning they are 3-dimensional. Standard form for a hyperboloid is x squared over a squared plus y squared over b squared minus z squared over c squared equals 1. X and y are the same as in a 2-dimensional model, but c is what determines its depth. A, b, and c affect how the hyperboloid stretch or narrow. This equation only shows a section of a hyperboloid because a real hyperboloid actually goes infinitely in all directions. The hyperboloid is one of the most complicated quadratic surfaces. Usually only taught in Calculus 3, its construction in nuclear power plants is a testament to the knowledge of the mechanical engineers that build them.